robotic optoelectronic testing platform for nuclear fusion experimentation will provide a way to characterize radiation data in a more efficient and accurate method. The origins of our project begin inside the Lawrence Livermore National Laboratory compound, located at the National Ignition Facility. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion. This research will provide global security, enable clean energy, and advance our understanding of our universe. Currently, there is high demand for better electronics during subcritical nuclear experiments. The main reason being that during these experiments, data is lost due to electronic failure from high levels of nuclear radiation. This leads to expensive overhauls of data acquisition equipment that cost taxpayers hundreds of millions of dollars per year. The need for better materials to place in these high-energy environments is necessary for understanding our nation's nuclear stockpile. Dr. Kevin Sun, the team's advisor, is conducting material research here at the University of Nevada, Las Vegas. These materials, or more specifically gallium nitride, is becoming a popular testing material for nuclear research. Gallium nitride is a very durable, mechanically stable, high-voltage semiconductor material which makes a great candidate for these high-energy environments. Working closely with Dr. Kevin Sun's electrical engineering team and NIF scientists, we machine test fixtures for gallium nitride photodiodes. These photodiodes are placed only 3 meters away from the target chamber center. It is here at the chamber center where an implosion of a deuterium-tritium fuel pellet is shocked with high-energy lasers to compress and ignite a fusion process. The lasers deliver over 1.9 megajoules of energy with an estimated temperatures reaching well above 35 million degrees Celsius. This is more than 2 times the temperature of the sun. These gallium nitride diodes must be tested pre- and post-experiment to see the effects of the high-energy neutrons. The current manual test setup has an experienced lab technician conducting 7 various tests to determine the effectiveness of each diode. It takes approximately 3 weeks to run a full characterization of a test specimen. This is extremely inefficient and time-consuming. One major concern for speeding up the process is to reduce the effects of radiation annealing in the semiconductor material. It is crucial to obtain the data as quickly as possible after nuclear fusion implosion because the annealing effect is a function of time. In other words, as gallium nitride cools off from the radiation, unwanted physical or chemical properties may become present and skew data results. This has become a hindrance for more frequent experiments at NIF and is creating bottlenecking in data acquisition. Scientists are losing data as soon as the fusion process is stopped. It has become a race to obtain data as quickly and efficiently as possible. To fix this problem, we designed a way to automate this process. The project includes extensive mechanical design, analysis, and optomechanical mounts. During the design and machining phase, the team had 7 different SOLIDWORKS revisions that drastically improved the structure and functionality of the platform. One major improvement was the addition of the cross brace bracket that increased the stability of the structure by 45% and decreased mechanical vibration by 43%. Using computer numerically controlled 3-axis machine in combination with Mastercam's X7 software to produce extremely accurate parts. This allowed the team to be confident that the machining tolerances of these parts are within plus or minus 1,000th from each other. This was crucial to ensure that the robotic testing platform provided results with the highest precision possible. Once fully assembled, students began integrating each of the tests into LabVIEW's primary hub called the front panel. The front panel is a primary user's way to interface with each of the testing automation processes. This is also where the individual diode patterns, diode wavelengths, test calibrations, and data collection will be accessed. To find the highest peak response, the team developed an intricate search algorithm that meticulously scans at a precision of 10 microns. In post-processing, the team studies characteristics of the diode by conducting 7 various tests. The first test is the forward and reverse bias curve. Biasing is an important base characteristic to determine maximum operating conditions of the diode as well as electrical circuit design parameters. It is also a way to detect the quality of the p-n junction or semiconducting material. Damaging neutrons from the implosion can have drastic effects on the intensity and spatial beam configuration of the diode. Therefore, it is key to map the characteristics using the beam profiler. Next, the team used the DET-10. This is a consistent way to measure the light output of the diode. Photoresponsivity is used to determine the efficiency of the diode to convert optical input into electrical output. Next is the emission spectrum test. This determines the wavelength at which the diode is emitting. It is an important design parameter when choosing optical sensing devices. The power meter test measures the electromagnetic power output of the diode. Results can determine if the diode can be used for electro-optical applications. The team achieved 3 major milestones. One of the objectives of the project was to increase the repeatability of the characterization of the diode. After conducting an analysis, the team reached a repeatability confidence level of 95%. In every characterization of the diode, the highest peak response is found. However, tolerances of this 40-year-old equipment has decreased over a lifetime of use. The team calculated the current precision of the linear positioner to be only 200 microns in the X direction and 700 microns in the Y direction. Regardless of the equipment limitations, the team was able to provide a product that is highly accurate and precise. With further advancements in technology, the precision and accuracy will improve. Secondly, a comparison between manual characterization of the team's automated test platform provided a data accuracy of 89%.
Most importantly, the team increased the productivity level of the characterization more than 5,000%, reducing data acquisition time from 21 days to just under 9 hours.
The addition of the automated test platform will become a small piece of the puzzle in developing energy solutions for fusion ignition, saving millions of taxpayer dollars and providing electrical power to the globe in a cleaner and more ethical process.